Okay, so we're back to this problem. All right, so we said that the thickness has to be an integer times the wavelength of light in the layer divided by 2. But they never give you the wavelength of light in a layer, because who knows? You know, they give you the wavelength of light in a vacuum, because that's what people know and what they measure, right? So now what you have to do is remember that formula that we learned a while ago, which I showed you a little bit ago. Oh, there it is. All right. So you have to use this formula. So the wavelength of light in a material, or medium, whatever you want to call it, equals the wavelength of light in a vacuum divided by n of the medium. All right. You have to remember that. So years ago, I had an exam, and I had a bunch of these questions, I don't know, 1 or 2 questions on it or something, I don't know. And for whatever reason, most of the students in the class forgot to use this formula. So they get all those questions wrong just because they forgot to use that formula. Bad, bad, bad. Okay, so let's do it. All right, so the thickness is m lambda layer over 2. Well, that's the same thing as m lambda vac over 2, over 2n layer, right? Agree? So wavelength of the layer, or the medium, is the wavelength of the vacuum divided by the index of refraction. Okay? All right. Hey, where'd it go? Uh-oh. Uh-oh. All right. Now notice it says find the 2 smallest possible non-zero values for the thickness. Okay? So here's our equation. The thickness is m lambda vac over 2n layer. So we want the 2 smallest. So that's m equals 1 and m equals 2. So for m equals 1, the thickness is lambda vac over 2n layer. And for the m equals 2, the thickness is 2 divided by 2, which is 1. So just lambda vac over n layer. All right? And I promise you, if you do that, plug it in, you get 183 nanometers. And for this one, you get 366 nanometers. Yeah, don't convert to meters. It's a waste of time, right? Because when you're talking about the, you know, these are really small, thin films. So just leave it in nanometers. So there you go. Okay, since I like these so much, we're going to do another one. If we were in class, you would do it. I would walk out of the class and I'd have you do it by yourself. Maybe we should do that. Yeah, why don't we do that? So be brave. Pause your video and you do it. All right, let's see, hold on a second. All right, so let's assume that you actually worked on this problem like I asked you to, and you did it, and now we're just going to do it together to make sure you can do it right. All right, so what's the minimum thickness benzene that results in constructive? See how they always say it when viewed at normal incidence? So we ignored that with our picture, right? All right, so a glass slide supports the film. Okay, first thing you want to do is draw the crazy exaggerated diagram. So this is air, n equals 1. This is the film, n equals 1.501, and this is the glass, n equals 1.620. Woo. All right. Okay. Like before, you have one ray of light coming in. It's really coming in perpendicular, but I don't care. So it comes in like that. and then it reflects like that. That's number one. Then it goes through, reflects, and there's number two. Okay? And this is the thickness. Don't forget that. Don't forget that. It's the thickness of the film. All right, close enough. Okay, here we go. Reflection number one is from air to film, 1 to 1.5. So there's a phase change of pi, which is equivalent to a flip of lambda over 2. So there's 1 lambda over 2 flip. Okay, radius number 2, that's where the reflection is. From the benzene to the glass, 1.5 to 1.6, small to large. There's another flip. Oh my goodness. So there's another half a wavelength flip. Okay, so look. This guy flips and this guy flips. So if they both flip, they're both the same, right? So if that was all we had, this guy flips and this guy flips, they're both equivalent. So we're going to get constructive interference. Okay, now let's see what they want. Oh boy! They want constructive interference. Awesome! All right? So right now, if we didn't have a path difference, we'd have constructive interference because this is exactly the same as this. They both flipped. But we do have have a path difference, right? So I should write down. We want constructive. We want constructive interference. And you get that from just reading it. Okay. So we want to keep, right now we have constructive. We want to keep it, but we get this path difference. So if we want to keep the constructive interference, we just want 2t to be m lambda, right? M lambda film. And then we're guaranteed to have constructive interference. Okay. Now, what do they want? They want to know the thickness of the film. That's what they always want, or not always, but almost always. So therefore, the thickness is m lambda film divided by 2. But again, they never give you the wavelength of the light in the film. They only give you the wavelength of the light in the vacuum. So we have to use this. So that's going to be m lambda vacuum all over 2n film. All right? And this one, it says the minimum thickness. Well, the minimum thickness is m equals 1. So we have m equals 1. So therefore, the thickness is lambda vac over 2n film. Now let's just do it. So lambda vac is 615 nanometers. Okay, 2n film is where? 1.501. And I promise you do that, you get 208 or 204, 204.9 nanometers. There you go. Okay, make sure you can do those. All right, last topic. Last topic. Beats. Beats. All right. Now it's not this kind of beat. Okay, so if you've ever gone to a concert, like classical music concert, I mean, you know, what does the orchestra do right before they start? Like everybody sort of sounds like they're warming up or something like that, right? So why do they do that for? Because they want to be in tune. Okay, so what happens, maybe you've heard this, what happens, let's say you have two people playing a violin, or I don't care how many people, everybody's playing a violin, and they're supposed to all play the same note. So they're playing the violin, and somebody's off. So they're not playing, they're almost exactly the same, but they're not exactly. So this is what you hear. You hear something like this. Wow, 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 something like that. All right? So that's called the beat frequency. You hear this loud, soft, loud, soft. So the beats occur when you have two or more sources, and they're really, really close to having the same frequency, but they're just a little bit different. So they're not exactly the same. So I actually have a demo. Well, not a demo, a YouTube video or something. So let's see if it works. Uh-oh, come back. Come back. Come on, don't do this. It's going to be troublesome. Yeah, darn it. Okay, hold on. There we go. Come on. Okay, hold on. Wait, come back. Stop.